Hello and welcome to our lesson on the conversion of temperatures from one thermometric scale to another. You are watching this on the Udimking Education Foundation Channel, your home for deep conceptual clarity in physics. In today's session, we are expanding past simple mechanical calculations. We are going to unlock the universal mathematical framework that connects any two arbitrary thermal scales together, giving you the tools to derive and solve any conversion problem from scratch. Let's get started. Why do we need a standardized system for temperature conversion? Think about it this way. Imagine trying to build a massive architectural bridge where half of your engineering team calculates distances in meters and the other half operates entirely in ancient cubits. It would result in an absolute structural disaster. In the realm of physics, temperature isn't just an arbitrary number on a dial. It represents an active thermodynamic state of matter. But here is the catch. We cannot measure temperature directly. Instead, we measure physical thermometric properties that change linearly when thermal energy is introduced. Look closely at the instruments running across the screen. On the far left, our standard Celsius scale measures the thermal expansion of liquid mercury inside a glass stem, anchored between 0 and 100 degrees. Next to it, the Fahrenheit scale tracks the exact same volume of expanding fluid, but maps it across a completely different grid, anchored between 32 and 212. But expansion isn't our only tool. Look at the third card, a constant volume gas thermometer. It determines changes in thermal states by tracking the pressure of a gas column measured in millimeters of mercury. And on the far right, we bypass mechanical expansion altogether with a platinum resistance probe, using a digital multimeter to read precise electrical resistance changes measured in ohms. All four of these laboratory instruments are submerged in the exact same water baths, reacting to the exact same thermal energy. Temperature conversion is our universal translator, the mathematical engine that allows us to speak a singular, unified scientific language across entirely different tracking instruments. To seamlessly translate information from one raw scale to another, we rely on a geometric method known as linear interpolation. We assume that our thermometric property, whether it is the column height of fluid in millimeters or the resistance of a wire in ohms, scales at a perfectly constant uniform rate as thermal energy rises. This means that the fractional position of a temperature reading relative to its total freezing and boiling parameters must maintain an identical mathematical proportion on every single scale. Let's derive this relationship visually. Look at the blue labeled scale column on the left. Let's mark its lower fixed point as A, its upper fixed point as B, and our current mystery reading as X. Now look at the orange labeled scale column on the right. We will map its fixed anchor points as C and D, and its target conversion reading as Y. Think of this conversion as calculating the exact percentage of a ladder climb. On our blue labeled thermometer, I mean the thermometer on the left, the distance our liquid has traveled from its baseline is simply x minus a. The total length of the entire scale ladder is b minus a. Naturally, the ratio of our partial climb to the total structural ladder must balance perfectly with our second thermometer. Therefore, on our orange labeled scale thermometer, that is the one on the right, our partial climb is y minus c, and its total structural ladder length is d minus c. By setting these two scaling climbs equal to one another, we unlock our universal master equation, x minus a divided by b minus a must always equal y minus c divided by d minus c. In physics, that structural denominator, the total distance between our freezing and boiling anchors, is known as the fundamental interval. Because this ratio of change remains absolute across all materials, you can use this blueprint to crack open any temperature conversion problem. Whenever you encounter a strange new thermometric instrument on an exam, don't panic. Simply isolate its freezing anchor, calculate its fundamental interval, and let this master ratio guide you straight to the solution every single time. Let's treat an example.